Okay, warm greetings. Good morning to all of you. I guess we've been seeing each other once in a while over the last 5 weeks, so we don't need any formal introductions. But nonetheless, this is a study abroad program we started last year, so most of the information here is not valid for you, so it's just a legacy slide that I have from the previous year. But nonetheless, the dedication still remains. I am from Georgia Tech and I work with one of the greatest dynamicians ever, Professor Dewey Hodges. Unfortunately, he passed away a couple of years back. But when we signed this study abroad program and I worked with the OIR, which is the equivalent of whatever international relations office you have in Georgia Tech, it was primarily as a dedication to him, and I continue to do that. He really enjoyed teaching this course, and I think I have that enjoyment as well, and I hope I can spread that enjoyment to some of you as well. Okay, so that's the whole idea of this, and I'm really glad compared to last batch, this particular thing, which I think is the major portion which is different from taking the same course in Georgia Tech on campus. I'm glad that many of you are doing it as a group. Thanks probably to a large extent to Tilak. So do continue doing that, because I think that is great exposure. I'm really glad you also went to the HAL museum last weekend. It's those kinds of things also, apart from the cultural exposure, things which are related to what we are doing over here. Of course, dynamics is a much more broader subject, so you see anything in motion, essentially the dynamics is there, and that's what you're essentially exposed to. But nonetheless, how we deal with dynamics, each country and each region in fact has a rich history of that. Unfortunately, most of us are aware only of the Western history of how people dealt with science in general, physics in particular, and dynamics even more particular. But I'll try to give you a flavor here and now in terms of how Indian traditions have explored dynamics as well, without straying too much from the syllabus of the course. We will get a flavor of that as well. Okay, so let me rush through some of these things. Of course, you know my name, and I've been a faculty here for almost a quarter century, at the risk of giving away my age. This is not it, giving away my age, but the lab that we work on is abbreviated as NMCAD lab, that you see over here, and it's important for you to know the meanings of each of these, so that when you see me talking about certain things, you also see where I come from, because the advantage of doing an undergrad program at a research institution like Georgia Tech or IISc is the advantage that you get, that the professors are also working on cutting edge research, and they bring a flavor of that in terms of the applications for whatever they are speaking about. It's not just all theoretical stuff that has no application, so there has some relevance to that, so you'll see that. So coming to this one, let me start at the middle. C stands for composites, and that's essentially, as you know, even though you have not probably had advanced courses on composites itself, you know that most aircraft and most flying vehicles today are made out of this particular material because of its lightweighted nature, to put it in a very, very laymanish term. But essentially, that's where we are heading to in terms of the percentage of the aircraft, both in terms of the weight as well as in terms of the volume, the structural weight that is increasingly being taken over by this material, whether it's passenger kind of aircraft or military kind of aircraft. So that's something that really is the focus of our lab. But we take it a step forward. Being in the academia, we have the freedom to dream and look at some level of imagination of things that may work in the next 10, 20 years down the line, which is where the next level of composites comes in. That's the letter N, multifunctional. We try to see that, unlike typical structural materials which go into load bearing, because that's the purpose of a structure, is to bear the load, to offer some strength, to offer some stiffness, to offer some stability. But can it do a little more than that? Some of the things we explore, for example, is energy storage. Can the structure itself develop as a battery? can the structure do some sensing and some actuation, so that it can be what we call as a smart structure, which is a very popular term, adaptive structures or smart structures, which again is a subset of the multifunctional composites that we deal with. Now, all of these, if you look at, really are not totally new. Whatever we do as engineers, as scientists, there's a lot that nature has already done over many millennia. We try to observe that and try to adapt that. Put it in very, very simple things. Almost everything, if you look at it, there is a background to it in terms of how our own human body and mind are designed. For example, if you have a microscope, the reason why we have it is because we can see. If we couldn't see, there would be no need for a microscope. Just that we can't see small enough things, so we come up with a microscope. We can't see far enough things, so we come up with the binoculars. Even far away things, we come up with a telescope, etc. Same thing when you're trying to do certain things with our hands. So that's as far as sensing is concerned, an example of sensing. An example of actuation is we are able to carry certain loads, but we can't carry beyond a point. We need cranes to do that. So essentially, whatever we try to do, or in our own business of aerospace engineering, we can move from point A to point B at a certain speed, or we can cover a certain distance, point A to point B, through maybe even walking or whatever. But at the same time, when we come up with vehicles, both on land, in water, on rails, and of course the ones which fly in air and space, essentially we are trying to do that in a much more efficient manner. We are trying to achieve that. Of course, you see migratory birds, the little that they eat, how far they fly. So that's essentially things from nature that inspire us. We can't blindly copy it, but we need to adapt those things for the work at hand, what we want to enhance. So that's essentially the way in which we work on multifunctional composites, things that can do sensing, actuation. Say, for example, you guys are used to a particular kind of weather from where you come. When you come to India, probably you experience a slightly different kind of a weather, but over a short period of time you adapt to this new situation. That's the greatness about the human body and the mind. If you're willing enough, it can adapt to any new situations. That's essentially what we try to bring into the structures as well, in terms of its adaptability to new environments, to new kinds of situations, where you're seeing that it is more efficient in those as well. To give you a very, very simple example, you know, we have here a group captain from the Indian Air Force, Nanjappa Hebale. So he works on really cutting edge problems. So for example, we have drones, as you are very familiar with. When you go for smaller and smaller drones, we get to what are known as micro aerial vehicles or nano aerial vehicles, where micro aerial vehicles are essentially simulating bird-like flight, and nano aerial vehicles are simulating insect-like flight, right? So when you're trying to do that, obviously there are many, many challenges that need to be overcome from all the perspectives of a typical aerospace vehicle, be it aerodynamics, propulsion, structures, controls. All of these are going to have huge challenges. Now, how do we go about adapting to that? If you take a single MAV in terms of a phase of flight, so it's essentially, let's say, taking off, it's let's say climbing, then cruising, loitering if it's like for a reconnaissance mission, and then probably descending, landing, etc. For each of these, you would see that the kind of wing shape that you're going to have, the cross-sectional shape of the wing, the planform shape, all of these will be optimal in a different way. Okay, so different so for cruise, some particular kind of an airfoil shape or a particular camber of the airfoil might be more appropriate or more optimal. Similar, which means that you're probably enhancing the lift to drag ratio or whatever, right? So same thing in the when it is let's say taking off, it would be an entirely different thing. Or if it's loitering, when you want to enhance the endurance, it's totally different thing again. So all of these, if you want to achieve on the same aircraft, you have to have what is known as morphing. Okay, and that's typically what you see in bird or insect-like flight. Also, of course, it's flapping instead of fixed wing, but essentially you're looking at the shape changing in the different phases of flight. So that's morphing, and that's another part of what we call as the multifunctional structures. Now, whether we have those multifunctional structures or not, the primary function still remains load bearing. You can't get rid of that. That has to continue happening. And when you're trying to do that in a kind of a challenging environment like aerospace, where you want really lightweight, otherwise you'll not even be able to perhaps take off, or if you take off, you can carry very little payload or to very small distances, what we call as range, or if it's like a aircraft which is meant for let's say reconnaissance, it has a very low endurance, so things like that. So if you really want to make it efficient, you have to make it take much more stress closer to what the materials are capable of. When you're trying to do that, you end up with structures which are extremely thin, and you would have seen when you're probably flying to Bangalore, you would have seen your aircraft typically the tip deflections are so large, it's even visible to the naked eye. You don't need any apparatus to see that there's so much of a difference, especially during takeoff, landing, etc., where the lift is fairly large. So when you have such large deflections, we have what are known as geometric nonlinearities, and because you're pushing the materials also to their extreme, sometimes they might touch the nonlinear limits of the material as well, which means that pretty much everything that we see in reality, be it in aerospace engineering or many other fields, are not really linear. Linear models are great for reading in a textbook and getting a kick out of it in terms of the joy of being able to solve a very simple problem. But when you are applying it to real life, things fail, and nonlinearity is the direction to go. And in doing that, we do both kinds of things, analysis as well as design. So a lot of our problems, we work with the industry, both the multinational companies, the OEMs like Airbus, Boeing, Bell Helicopters, etc. In fact, we'll see if some of those visits can be arranged towards the latter half of or the first half of July. We will see how that goes, right? So, and also there are lots of Indian companies like the Hindustan Aeronautics Limited, HAL. There are government agencies like the Defense Research and Development Organization, the Indian Space Research Organization, etc. A lot of work done by ISRO, for example, is highly regarded the world over in terms of its capabilities at very low level of resources, and still being able to achieve what others have been able to achieve with much larger amount of resources. And most of those people, especially the engineers and the higher level management there, are all trained from this particular institution, the Indian Institute of Science, which is celebrating 100 years. And this was in 2009, but now it's more than a century old. But this is an important point from a dynamics point of view also, because now we're talking about an entity called time, and that's going to play a critical role in our entire course in terms of what is going to happen with various things in terms of time. So in statics, for example, which is a prerequisite for this course, you've already looked at the interplay of forces, moments, and the space. So space as a dimension, if you're looking at, so at the most you go up to 3 dimensions. You could have the simplest problem in 1 dimension and up to 3 dimensions. Now we are bringing in a 4th variable with respect to which things can change, and that's essentially the time aspect that we are bringing in. And that's at this stage, I think I pretty much introduced you, and also I already talked about him in the email. Singepogu Chinababu is one of my PhD students, so he'll be your TA for this particular course. So any questions you have related to the coursework, the assignments, etc., you can ask him, and I'll also be available whenever you need to interact with me as well. So I think you've probably already familiar with him, because some of the lab tours, I think he was a part of that. So some of you would have already seen him. Okay, so this is as far as we are concerned. So I'd like to very quickly go through each one of you. What you understand when you say the word dynamics, not from the point of view of AE2220, because that's what we're going to do in the rest of the course. But maybe if you have an idea about it, you can talk about it too. But dynamics is a word that we very commonly use in English. Even in our day-to-day life, when we generally talk about dynamics, dynamics of even life for that matter, leave alone of structures and engineering, etc. So I just want you to very briefly, maybe in a few sentences, talk about what dynamics means to you. Maybe you can just introduce yourself with your name, and then you could probably suggest I'll just pass this microphone so that you can speak through that.
Hello. Okay. My name is Daniel, and I would say when I think of dynamics, I think of how something moves or changes, whether that's like an object or a system in the world.
Okay, so that's an important point that he brought out in terms of change. Okay, so when there is change, it has to happen in the backdrop of something, and that's the backdrop that we are talking about in terms of time. So unless and until things change, you're still in the realm of statics, the course that you've already done.
Hi, my name is Nafez. When I think about dynamics, I think about like a strong contrast, as you mentioned, with statics, where we may still be talking about rigid bodies, but the change in time may appear as like some kind of fluctuation, as like a wave, a sine wave or a cosine wave, based on the outside conditions.
Okay, good. Yeah.
Hi.
So the microphone is actually where the blue light is, so make sure you don't cover it with your finger.
Okay, I see. Hi, my name is Tilak. Dynamics to me is how forces interact with each other while they're in movement. If we say that could be anything from a normal object going from one place to another, but also could be between two people as well.
Hello, I'm Andrew. Kind of similar. When I hear of dynamics, I first think of like social dynamics, like the interactions between different groups of people.
Yeah, that's a very important point that you brought up, Andrew, because that's something that tends to get ignored from us engineers usually. We forget that we are part of the society and social beings to start with in the first place, human beings and then social beings. So we are always talking about the systems that we work with rather than ourselves. And as I just mentioned, 2 examples of sensing and actuation. A lot of what we do in engineering actually comes from what we do ourselves with the body. So and what we do with others who also we interact with at a physical level, which is at the body level, and so that's social engineering and social dynamics. Yeah, go ahead.
So my name is Gracie, and when I think of dynamics, I think of forces interacting, but it's movement. So it's somehow time is affected or time is in that, and I don't know much more than that, so I'm interested to see what we'll learn.
Can I just add one?
Yeah, please. Yeah.
Dynamics is also something that's being taught here and is one of the hardest courses there is to learn.
That's good. That's a good one. Yeah.
My name is Riley, and when I think of dynamics, I think of something being dynamic, and I feel like that's very like free-flowing and like has a lot of movement.
Absolutely. So that's a very important point that you brought out because many times when we don't understand a word in engineering or English for that matter, we can look at some of the derivative words which we might actually be using. So we may not understand dynamics as a noun, but dynamic as an adjective is what she pointed out, that we commonly use a particular person is highly dynamic, at least at a given point of time. So essentially we're talking about as he pointed out, the change that is coming, and the change for the better, if it is for themselves and for the others. Essentially that's an appreciated quality of somebody being dynamic.
My name is Vitti, and I would say to me dynamics is, well, when I consider in comparison to like statics, we studied systems that were essentially at a standstill. Either they were subject to like zero acceleration, or they're moving at a constant velocity. I'm thinking in dynamics we're probably looking at systems that are actually moving like with some degree of acceleration, and in relation to time, seeing how those systems evolve with time.
Yeah, good. I'm glad you brought out the concept of motion when some things are moving, and I think Tilak, one of you, pointed out in terms of the forces. So these are the two things that are going to be interplaying with each other, which is what we're going to study. In the first part, we'll be studying what Vitti talked about, is essentially the motion itself, without having to explicitly talk about the what is causing it. And then we'll bring in what Tilak talked about for the second half of the course, where we'll see what is causing that movement, and we'll see how they are related to each other.
Hi, my name is Lalita, and to me, dynamics is, I think of like classical physics and how we study the motion of objects, but there are a lot of assumptions that we make, like this is constant, it isn't changing, or such and such. We just pretend that a lot of stuff is not changing at all, and I'm assuming in statics we can't make those assumptions anymore.
Right.
So yeah.
Right. It's a very important point you brought out, because there's something called quasi-statics as well. Okay, so quasi-statics is where we are trying to, as she said, Lalita, the body is actually moving, but we pretend that it's not moving. So for example, when an aircraft is cruising, it's maintaining its altitude, it's maintaining its speed. So a lot of things can be dealt with almost like it's a static problem. So that's what we call as quasi-static. We're just equating the lift to the weight, the thrust to the drag, and then you're trying to do a little bit of dynamics related to that. But in reality, there can be disturbances, there can be pilot controls, and various other things based on the actual whatever is the flight plan, and all of these can induce certain changes in the forces and moments, and therefore the equilibrium can be lost temporarily, and then that creates, when there is a lack of equilibrium, we bring in a different kind of a force or a moment, what we call as the inertial forces and inertial moments, which essentially bring in what is known as accelerations. And accelerations could be either translational accelerations, changing the speed, or it could be rotational accelerations, where, because we are involved with a body, not a point, so we can have the changes that are occurring with the orientations, and those will be typically caused by torques. So all of that brings in play. Okay, so I'm really glad we got a picture of what each of us thinks about dynamics when we just hear the word. Of course, it was a short input from you, so obviously you wouldn't have said all that needs to be said about this, which you know, and we will come across some of those things as well when we tend to go forward, and we'll see how exactly those things fit in terms of the formal study of dynamics as part of AE 2220, and we will see how they're kind of correlated to each other. So that's essentially what we will be doing. So let me start with is everybody able to see this? Yeah, so this is what we are trying to study, and where we have come from is in terms of your course on statics. So we'll take that for granted, whatever we have done over there. So that was the other branch that we already had. Okay, so here we are not talking about dynamics in its more generic term, like the social dynamics that you talked about, but nonetheless, very interestingly, if you look at it, some aspects of it, or in fact many aspects of it, will be applicable to those as well. Okay, just that we are not talking about it explicitly, but inherently there's a lot of learning that we can do from one branch to another branch. And this is something I really learned again from my advisor, Professor Dewey Hodges. I'm sure all of you are aware of the brown bag lunches which take place at Georgia Tech. Irrespective of which field the talk was going on, he used to always be there with his brown bag. And some of those interactions with the speaker, actually in a completely, totally different field from what he works on, have led to research collaborations and even very good papers out of that. So some things that we might be stuck up on our work, somebody else might be doing in an entirely different field, almost on a routine basis, day in and day out. Just that we need to understand how they do it and not blindly copy, as I said earlier, but adapt it in an appropriate way to your problem, and lo and behold, you might be able to solve something that you were stuck up on for so long, right? So that's the takeaway from statics to dynamics, which we will see, where, as I said, you had the understanding of how objects are and the cause of the dynamics, which was the force, which was already there, but it was in an equilibrium in some sense, either statics or, as Lalita pointed out, quasi-statics. but we want to see when that equilibrium is kind of disturbed, what exactly happens, and that's the dynamics. But even before we get there, in terms of the play of forces, as I said, we are going to do this in two parts, and I already briefly mentioned that. One is what we call as kinematics. Where we will be talking about just the description of the motion without worrying about what caused that motion. It could be a force, it could be a torque, a combination of set of forces, a set of torques, or both, but we are not really bothered about. We want to see, can I describe the motion, how it is right now, how it is changing with time. All those things comes under what we call as kinematics. And once we are very comfortable in the zone of seeing how we can describe any kind of complicated motion, then we will go on to the cause, what caused that. Okay, so here it's the description of motion. And here what is typically called as kinetics. Sometimes the word dynamics itself is used to refer to just the kinetics. It's a question of different schools of thought of how they deal with. But from our point of view, throughout this course, when we talk about dynamics, essentially talking about these two aspects. One is with the description of motion. Here it's the cause of motion. So the common word, of course, is motion, which essentially brings in the need for, in the context of the differential equations course that you have done, for example, you know there are two kinds of variables, dependent variables and independent variables, right? So dependent variables are your unknowns, which you want to solve for by solving the governing differential equations and or the conditions that apply to it, which could be either boundary conditions in a so-called boundary value problem or initial conditions in a initial value problem. You'll see the latter kind quite a bit over here. Okay, but even before we get to that, we need for an additional independent variable. So in other words, we already had x1, x2, x3 as the most complicated form of independent set of variables that you could have in statics. The simpler ones, of course, would be either two-dimensional or one-dimensional, where you have either only x1, x2 or only x1 that you're dealing with. But even in the most complicated problem of statics, there are only three independent variables that you have to deal with. And the simplest of them, you had only one independent variable, in which case you didn't have, let's say, your x2 and x3. So when you have just one independent variable, the governing differential equation that you get, what is it called?
Ordinary?
Yeah. So you have what are known as ordinary differential equations that you can deal with when you have just a single variable that you're dealing with. In many cases, the statics problem may not even be posed at that level, because it's just the equilibria that we are looking at, force, etc. Most of it is solved as algebraic problems. Okay, you're not even getting into the differential equations, but you know that once you bring in the reality check, like what we are dealing with in aerospace engineering, where we know that none of the bodies are rigid bodies. You can deal with the aircraft as a whole as a rigid body to understand the rigid body dynamics to a large extent. But then when we want to do some really meaningful work, we have to bring in the flexibility of the various components, and therefore what is the deformation that is taking place, which you will study as part of the deformable bodies and the structural analysis courses that you have at Georgia Tech as a requirement, right? So now we want to see what happens when we introduce already x2 and x3. This will become what is the other thing other than ordinary when you have more number of independent variables, partial, right? So what we call as PDEs. So that's a possibility when you had x1 and x2 for that matter, even without x3, it would lead to partial differential equations, making things a little more complicated to solve. Some of them, of course, are amenable even to analytical solutions, but as it gets more and more complicated, you want numerical solutions for this, which you implement using what are known as finite difference methods or finite element methods, etc. Right? Now, on the other hand, even in the simplest problem here, you already have two variables that are coming up. When you have only one variable in space, but you still have the temporal variable. So we have a new kind of variable which we call as the temporal variable, as opposed to the spatial variables that we had over here, right? So these are spatial variables and these are temporal variables. By spatial we mean in the three-dimensional space or 1 or 2D space that we are dealing with. And when you're talking about the temporal, we're talking about the dimension of time. And in the, already when you have a 3D structure over here that you're dealing with, a 3D space that you're dealing with, and then you come in and bring time, you've come to a 4-dimensional thing. Already the human mind is not able to imagine what you're talking about, okay? Just that time is an experience in our life. We are born, we die, in between we move from places to places, various things that we do, all of them involve these elements of space and time, and all of these are part of our life's experiences, and the same thing is carried over to the engineering structure. And very interestingly, there is a quality that is similar to whether you're talking of x1, x2, x3 on the one hand, the spatial variables that is, and t or the time on the other hand, which is the temporal variable. There's a quality that is already evident, which is common. There are many things else that we will see as we go forward, and that thing which is the commonality is that both are independent variables. Okay, they are not the dependent variables that we are solving for. We are not solving for time. We are not solving for x1, x2, x3. That's the field in which this whole thing is happening. And so on that domain, we are trying to see what are the other things that are happening because of the causes, namely the forces. How is the motion overall taking place of a single particle or a rigid body or a flexible body or a set of them, and how they are interacting with each other is all that we are going to see. Now this quality that is common between them, that is essentially you're talking about the both of them being independent. So the independent nature of your x1, x2, x3 on the one hand, and the time t on the other hand, is very interestingly in the way in which we understand it from an Indian perspective is dealt with. We have this word kala, which essentially talks about the domain in which things are happening. That includes both space and time in the common parlance. Most people think of kala as just time, but actually kala is used in a lot of places for the spatial dimensions as well. So in other words, it's interchangeably used, the same single word for both. Of course, there are many other words for each of them, but when they talk about the science over here, the way it developed, a lot of that science, both in statics and dynamics, has been done with that aspect in mind, that yes, these are the independent variables which create the field in which all the other things are going to change because of certain causes, and then how do we handle each one of them becomes very simple. In which case, we don't need to have that distinction of what we called here as boundary conditions, and therefore resulting in what we call as a boundary value problem, right? So that's essentially what we're talking about. A particular structure like this has certain boundaries. It starts at a particular location, ends at a particular location in this dimension called length. In this dimension, it's the breadth. In this dimension, it's the height or thickness, if you're putting it this way. So essentially, you're talking of L, B, and H. These are the three dimensions in which you have boundaries, and you specify certain conditions on those boundaries in terms of, let's say, I'm restricting the deflections in some locations. I'm probably restricting, let's say, the rotations in some other locations. These are what are known as geometric boundary conditions. On the other hand, there are other boundary conditions which are in terms of the load that you're applying. At some location, I know what is the force that I'm applying, or what is the moment that I'm creating, or it could be a pressure, a distributed load that you have. Or when it's an, let's say this is an airfoil and it's part of the wing, there's a flow taking place, and therefore not only is there a pressure distribution but also shearing stress distribution in the boundary layer that is created around the airfoil, right? So all these are boundary conditions. Equivalent to that, what we have here are known as the initial conditions, and leading therefore to what is known as an initial value problem. Okay, so now a lot of books and courses are invested on studying this separately and this separately, but once we understand what really is happening, you can be blind from a mathematical perspective or the solution perspective to whether it really is happening with space or is it happening with time. And many times these can be interchangeably used as well, and it's really beautiful when we look at a few examples later on. Things might seem a little hazy right now as to what I'm speaking, but you will see as the course progresses, we will take up a few examples and I'll show you the interchangeability of spatial dimensions and the temporal dimensions to see how things are occurring in a very similar manner. And therefore, if you understand one, that is, if you have done reasonably well in your statics course, not in terms of the grade, but in terms of the understanding of the subject, then chances are very high that you will be able to do very well in dynamics, in spite of Tilak pointing out that this was one of the most complex or complicated courses over here. Okay, it's a question of perspective, how you try to gather information about the course, and not just gathering information as a knowledge, but then converting into a wisdom where you're trying to apply that knowledge. Because once again, coming to the Indian perspective of learning, we have it as three parts, what we call as Shravana, Manana and Nididhyasana. Shravana is like what you're doing right now, you're listening to me, okay? So, or you're reading a book, or you're watching a YouTube video about this. So then you're essentially getting inputs. That's your Shravana. But for most people, learning stops at that location, which is the sad part of it. But if you're really interested in the subject, what would you do once you have seen a video, or once you have attended this class or read a book? You would start thinking about it again and again, okay? So essentially, those concepts are getting ingrained in you, what we call as manana, the reflection that you're doing. It's not just inputs, the listening, but also the reflection about it. And the final aspect is the nididhyasana, which again, even if people do both Shravana and Manana, that is listening and reflection, they fail to do the third one, which is application. So essentially applying it to a real life problem and therefore seeing how it works, okay? That's the proof of the pudding. We do a lot of research, as I said, and every one of those researchers for the industry is guided by a problem that the industry is facing at that point in time. So when we see that something that we have contributed actually is on a flying aircraft or a flying helicopter or a flying rocket today, that's a huge kick for us. And when it can also get us a publication, it's a win-win kind of a situation. So that's the essential way in which our lab progresses, and that's the way in which this teaching also will be, where I'll not only be talking about the concepts, the equations that govern them, but also the third aspect that I just introduced to you, Nididhyasana, where you're trying to see the real life applications, so that you're then a little more involved with that. Because see, the whole idea is when you learn better when you're involved with something, okay? You don't get entangled with it, but you are involved with it, means that a part of you, a part of the subject has become a part of you. So then you really know that you are enhancing your learning. And learning is something that you do not only as students, but even at my age or much older, learning is something that never stops. If you stop learning, you're like dead men walking. So that's the kind of importance that we give to learning. And as I said, learning involves not only in inputs, but also churning that input, analyzing it for yourself, and then applying it to a problem. So all three aspects, when it's done, this learning stays with you for long, much longer than otherwise, and then you can apply to fairly complex problems which are observe day in and day out in our field. A very challenging field that we are in, Department of Aerospace Engineering, or the Woodruff School of Engineering, Aerospace Engineering that you talk about. We deal with cutting edge problems, and many of the solutions that we provide in aerospace engineering, whether at Georgia Tech or IISc, carry over to many other fields because they're spin-offs as solutions as remote as what people might not even consider, like medical fields. There are a lot of applications from aerospace which have gone on to create humongous improvements in how the health of a individual is taken care of. So those are the things that we would like to see in terms of the carryovers or takeaways, right? Okay, so now kind of summarizing what we talked about here in my not so legible handwriting, let's try to put it across in a more clearer fashion. The whole course of dynamics, not only AE2220, but wherever and whichever way you learn it, whether you're told about it explicitly or not, essentially consists of these two. Okay, people might use different terminology for it, but more often than not you will find this. And in fact, very luckily, a lot of textbooks on dynamics have been written from Georgia Tech by Georgia Tech professors who were professors in the past. And we've had a rich heritage of dynamics in not just my advisor, but many others who have worked on. And in fact, one of the books which is, we will talk about it, which is used as a textbook by others who teach this course on campus, is also written by two former professors of Georgia Tech. Okay, so we already seen what these two mean. But if we look at the English is a very, very interesting language, even though it has a much shorter history compared to most other languages in the world, especially in the country that you are. We have orders of magnitude difference between the age of English and the age of many of the languages that we speak on a day-to-day basis, and also the foundation of them all, the Sanskrit. But even in English, there are a lot of things that you can observe, and these things can actually influence a lot of things that you do. One thing is the word dynamics is coming from a Greek word, dynamis, which essentially means power. And power, as you know from other subjects that you have learned, is essentially the rate at which energy is spent or the rate at which work is done. Okay, so it's essentially in SI units, you would say joules per second. So that's essentially the speed. So you talking about time over there, and you're also talking about the cause that we talked about, the cause of motion as forces and moments. But what are they actually doing? If the force and moment are not making the point of application of the force or moment move in that direction of the force or moment, then really they're not doing anything at all. Okay, they're as good as not being there. So which essentially means that what is the cause of motion is actually, if the motion actually happens, is essentially doing some work over a period of time, and the rate at which it is doing is what that word, the original word for dynamics in the Greek language, actually means. But on the other hand, what I'm more interested in is in terms of the word play over here. If you look at the spellings of these two components of dynamics, they're very, very similarly spelled, and the only difference that you have is in what you have in the middle. Right in the middle over here, you have this word. There are 4 letters over here, 4 letters over here, and there's a two-letter set that is in between. And if you recollect from high school, what you learnt as Newton's law of motion, the second one there, force is equal to mass into acceleration. Okay, so that mass into acceleration is actually contained within this. Okay, so this is something that I had not thought of myself when I was teaching your previous batch. It just occurred to me as I was speaking about it and I was writing these things on board. You see that kinematics is something, as I already told you, is a description of motion, where you're not talking about the cause of motion, but that cause of motion is the force, which is equal to your ma. In other words, it's built into it. Even though you may not be talking about it explicitly, without that the motion would not have happened and you wouldn't be able to describe the motion. Just that you are not bringing it out to the open, it's all contained within, you are only describing the motion. Therefore, your m into a, the mass into acceleration, which is the force, or for that matter in a generalized sense it includes moments, couples or torques, then all of that is contained within the kinematics. We are only talking about what happens to a particular particle moving from one point to another point, at what speed, how is it accelerating, etc. All those we are talking about, but without saying how it is caused, because all of that is contained within, whereas you don't have that M&A over here. So in other words, you've taken that MA out and brought it out explicitly to deal with kinetics, where you have to talk about now the cause of those cause of that motion, which is essentially your force and moments, and then you see how the kinetics comes into play. Okay, so these roughly will probably constitute half a portion of our entire course, in terms, because unless and until we understand this well, sometimes people don't give much importance to this, they directly jump to kinetics, then you lose out a lot, and the understanding of kinetics also suffers, because this is like a bedrock foundation. As much as statics was important for you, which is why it's called a prerequisite, the first half of this course where we are dealing with purely the description of motion without the causes, then or rather causes implicitly contained within, then that is very, very essential in order for you to understand kinetics later on. Okay, I might be going in the flow because I really enjoy teaching. I might even continue for 3-4 hours without stopping. So feel free to interrupt me whenever you have questions or anything that you would like to know a little more about. So or something that you know which might be of interest to the rest of the class, which I may not have talked about. Please bring in that flavor into the class so that all of us can learn together. Because I not just believe but have experienced that teaching is the best way to learn. So especially when I'm teaching very smart students like from Georgia Tech or IISc, these are the top schools in our own countries, and the kind of interactions we have, the questions that you ask, and or the work that you have done, and when we exchange information about it, there's a lot of learning that happens in me. I try to look at things from a different perspective. Same things I might have been looking at a totally different perspective earlier. So it's very important from all of us, for all of us, that whenever you feel like saying something, please feel free to do so. Yeah. Anything that you have right now in terms of questions? Okay. Yeah. Sorry. Yeah. So the second thing that we'll have been doing, and this is something in terms of the pedagogy or the way of learning in the Western world, that whenever we want to learn about something, we break it up into parts. If you want to learn about the human body, you learn about the heart separately, lungs separately. So you have a cardiologist, you have a pulmonologist, you have an ophthalmologist, you have the orthopedic, and so on and so forth, right? You're breaking up things into parts and then trying to, which is what analysis is all about. So you're trying to analyze things, but then when you're trying to synthesize the whole thing, that is, you've broken it up into parts, which is fine because it's a complicated thing that we are dealing with. We can't understand probably the whole thing if you break it up front. Okay, so therefore you have to break it up into parts, and the same thing we do with the case of the aircraft, right? In fact, probably one of the greatest services, or looking at it from a different perspective, the greatest disservice which the Wright brothers did in 1903 when they flew at Kitty Hawk, is that they separated out the propulsion system from the aerodynamic system. So in other words, you have an engine which offers propulsion, you have the wings which offer your aerodynamics primarily. Of course, you have the tail and other things, but essentially that's what it is. But if you look at all the natural flyers, be it birds or insects, it's the wing itself, through the flapping motion, which is used both to create the thrust as well as to create the lift. Okay, so when you're trying to do things a little more holistically like that, things can be far more efficient. Just that our goals were quite different. We wanted to fly either much farther or much faster and take more payload with us, etc. So when we wanted those kinds of things, the separation really helped. But it's always good when that is not needed to go back and see how nature does it, because nature has done it for many, many millennia. We engineers have done it for a few centuries at the most. Many of the things that we talk in aerospace engineering just for a few decades, like composites, for example. So the learning that we can get by going back to nature is phenomenal. Okay, but nonetheless, we will look at it from a Western pedagogic style over here throughout this course. Once in a while, I'll bring in that flavor of the Indian thing because you're here taking advantage of that. But just like we broke up dynamics into two parts of kinematics and kinetics, in terms of the motion, we now talk about the motion of what? The motion of the simplest thing that we can really talk about is so-called particle. Any of you can mention what is the difference between a particle and a point? Absolutely. So that's the thing. So essentially, from a geometric point of view, a particle is also a point, but it has a certain physical attribute to it. As Nafis pointed out, it's bringing in that aspect of the mass to it, okay, which makes a huge difference in dynamics, as we shall see when we go to the equations governing it. But whether a particular particle has mass, how much mass it has, or is it massless, will make a huge difference in terms of the overall behavior. So that's the simplest thing that we'll go to. But the whole simplicity that is coming, you can't in reality have a particle, okay? So though there's a huge branch of physics called particle physics, you're talking about the subatomic particles, you're talking about trying to understand how they behave, how to create them, and how to their dynamics interplay between each other, etc. But ideally speaking, the particle should have a zero dimension, no length, no breadth, no height. So essentially you're talking of a point from a geometric sense, which is a zero-sized entity, okay, which you don't have. If you, and as Nafis said, it had a mass, the mass is finite value, the volume is zero, because L, B, H are all zeros, okay. So then you have mass by volume is the density. So you're talking of an infinite density kind of an entity, which is, or material, which is not in existence, right? So, but nonetheless, these kinds of concepts really help us get to speed on more and more complex things that we will deal with later on. So it's we have to bear with that and try to understand those aspects as well. And most of the time, it's all in a relative sense, okay? If you're talking of the aircraft, it could be a typical aircraft that you flew in will be of the order of a few meters in length, the fuselage length, the wingspan, etc., right? Even the height. But if you're talking about it, where it is flying, it's flying in the Earth's atmosphere. So compared to the size of the Earth, the aircraft is like a particle, okay? So the simplest dynamics model of that would be just to deal with it as a particle, which is what the equilibrium equations that we talked about. Lift is equal to weight, the thrust is equal to drag. So essentially you're dealing with that. So essentially reducing, because it's not the actual absolute values of a few meters wingspan and fuselage length, but compared to the diameter of the Earth, it's which runs in like 6,400 kilometers or whatever, you're talking about just a few meters, and therefore the relative size is very, very, very small, and that's why it's negligible, and therefore you can treat it as much as a particle. But then you see that that's not sufficient for a lot of things that the aircraft does, and then you try to go beyond the particle model or a point for the geometry to a finite size, and that's where you come up with bodies. And throughout this course, whenever we talk about bodies, though in this slide for the later points I will explicitly state it, we are talking about rigid bodies. Anybody who can say what we mean by this qualification of a body being rigid as opposed to anything else? Absolutely, yeah. So you have on the one hand rigid bodies, you have on the other hand flexible bodies. Once again, in reality, everything is flexible, okay? There's nothing that is not flexible, just that the level of flexibility can be different. Some are more flexible than the other, and so therefore, once again, the relative nature comes into play, and therefore, certain bodies can be dealt with as a rigid body to start with. But then when you go to more advanced courses like structural analysis, etc., you will free up this particular assumption or wrong assumption that you're making in order to be more true to life, what is observed in the actual engineering structure, okay? So now that we have understood, when we finish studying particles, we would have understood how to deal with a particular point having a finite mass. So then we want to carry over that knowledge, just like we wanted to carry over the description of motion in kinematics to the cause of motion and therefore the interaction between them. Here also, the understanding of particles that we have that is zero-sized entities of a finite mass, then we want to carry over to bodies. We introduce a concept called the center of mass. The center of mass is something, again, you're very familiar from high school physics, even probably middle school physics. Essentially, you're saying there's a mass distribution, there's a particular location within that, or sometimes even out of that, physically speaking, that you could have this. For example, if you have a ball, the center of mass is at the center where there's no material actually, okay, because the whole ball is hollow, right? Then you typically have, or filled with air, whatever. So then you are typically looking at this mass center as the equivalent of the particle that we did. So in other words, we know it's not zero sized, it is finite sized, but then I'm lumping it all together at a particular location, and therefore a lot of, or a major portion of the motion description can actually be handled over there. So a lot of these things we'll be doing even before we get into kinetics in kinematics itself, to make sure that we understand, we can describe the motion very, very clearly, and then we can then bring in the forces and torques and see how they change, right? So that's as far as the motion is concerned. So once again, you see the pedagogical style that we use, the Western way of learning. We break up a more complex entity into simpler entities. So we broken up motion in general into motion of particles and motion of the mass centers of the rigid bodies. And one takes the learning from the other. The third thing that then, now that we have understood the rigid bodies reasonably well, we will start talking about the overall motion of the rigid body, because it's not just, the rigid body is not just its mass center. Mass center is one idealization of that, which helps you to understand the translation of the body. So this body is moving all over the place, so its mass center is also moving along with it. So I know by looking at the mass center's movement, I know how this body is moving. But the same body could also be changing its attitude as it moves, with that I'm not able to get purely from this. So I need to bring in the so-called rotations as well, which really didn't make any sense with a particle. When a particle rotates, it doesn't make any sense, because it's like a rotation of a point. It's zero sized, so there can be no so-called concept of a rotation of a point or a rotation of a particle. It's only because you have moved from a zero size to a finite size, then you have the need to deal not only with translations but also rotations. And as always, we want to start with the simplest way. In statics, as I said, we started with ordinary differential equations with just one spatial variable, and then went on to get in the other spatial variables as well. Same way in the case of the rigid bodies, we know that this, just like there are three translations, there are three rotations as well, about the three axes that you can have. Like in the case of the aircraft, for example, you know that there is the pitching motion, there is the yawing motion, and there is the rolling motion, right? So these are the three different motions. We do not want to get all of them simultaneously, okay? So we start with the simplest kind of model that we can have. Just like here, we started off with just one degree of freedom, but essentially independent variable. Here we are talking of just one rotation at a time, because if we think all the motion is happening in this plane, let's say the plane of this screen that you have, projection screen that you have, then you see that I can have a motion in the forward direction, I can have a motion in the vertical direction, okay, and then I can have one rotation which is about an axis which comes out of the board or out of the screen or into the screen, depending upon the coordinate system that you have. You essentially are bringing in that particular aspect. So in moving from particle to bodies, the complication is because of rotation, but in reality there are three rotations. Like in the aircraft we discussed about pitch, roll and yaw, but we want to bring in only the one rotation at a time, which in this case of the aircraft example will just be the pitching motion, because it will just be the climb that you have as a one particular degree of freedom, the forward motion as one of the degrees of freedom, both of which are translations, and the only rotation you are bringing in is the pitch rotation. That changes, of course, your angle of attack also. It has the potential to change its angle of attack, and therefore the lift distribution, the drag distribution, etc., and therefore make it change its altitude. For example, if for cruising to start with, then you can either descend or ascend depending upon how the pilot moves the pitch stick forward or backward, right? So all of that we will then be able to deal with when you're talking of planar motions. In other words, even though we are looking at very simplified problems, they have implications in even in aerospace engineering, which is what is the connect that I want to bring. So it's for no reason that we call this course AE2220. It's not just any COE 2220. That would be a College of Engineering course, which will be general for all the branches of engineering or many branches of engineering. No, here we are talking of aerospace engineering. So I really want to bring in the connect between dynamics as a subject of physics and dynamics as applied to the aircraft. And therefore, even though you will have a separate course on aircraft dynamics later on, you will be looking at the actual governing equations there, etc. There are certain aspects of it we will cover in the second half of the course here itself to give you a flavor of the examples or applications that we are going into, right? Once that is understood, and very interestingly, in the case of the aircraft, typical aircraft design, you have a plane of symmetry in that XZ plane, where X is along the length of the fuselage and Z is along the vertical direction. You're essentially having that XZ plane as a plane of symmetry for the aircraft. In other words, you have one half of the wing, the starboard and the port on either side, and then you have the tail, etc. Of course, when it's cruising, let's say you're not deploying the rudder or the ailerons. At that time, you're only using the elevator, and essentially you're trying to move within the plane, a particular vertical plane, and therefore there is a 1:1 correspondence, especially for the aircraft, which is why when you actually look at the dynamical equations treating an aircraft as a rigid body, you will see that it breaks up into two coupled systems which are not coupled with each other. Okay, so they get decoupled in that sense that one set of three, which is the forward motion, the vertical motion and the pitch, come under this. The other three, which is essentially a roll, yaw and the sideward drift, which can happen, for example, if it's a gust which is having not in the plane but out of the plane, any gust that is there, you essentially look at a sideway drift, or you could actually induce it purposely based on certain maneuvers that you would like to do, or a change in the flight path that you would like to do. In which context we have a lab tour coming up where we'll be looking at a lab which primarily deals with path planning. How do you plan the path? How do you, once you plan the path and you know what's the path that the particular flying vehicle needs to take, we will then look at what is the guidance and control logic that needs to be built in order for this to happen, even if it's an autonomous vehicle without a actual human pilot either flying inside or from outside remotely, right? So, but the whole idea is that we have dealt with the complication of rotation by bringing it one at a time, that is essentially the pitch motion. But then now that we have a confidence of dealing with it, we bring in the roll and the yaw as well, which is the overall 3D motion of the rigid body. Though I'm giving it to you as an example from an aircraft parlance, this applies to any body, any kind of dynamics, not only in the transportation sector, but overall anything, even as small motion as, let's say, this particular building. In the case of an earthquake, if it is going to just, let's say, vibrate a little bit, even that kind of motion, all of that can actually be covered in this. Just that we will then have to relax one more assumption, which is rigid, which we will not do in this course, because that's a whole different ball game. We are bringing in the elastic nature, or as one of you pointed out, in terms of the flexible nature, the flexibility into picture. Then things become a whole lot different, because now you cannot deal with just the mass center and the rotations and be done with it. Each point in the aircraft can move quite freely with respect to each other. Not freely, there is a restriction in terms of the internal forces and the external forces on it, but to some extent you have to, just by knowing the motion of a particular point on the aircraft, you cannot say, and its rotation, you cannot say about all other points. Whereas the rigid body, if I know the motion of the mass center, which is its translation, and I know all of those 3 degrees of rotation, the orientation, I can say everything about every point on that aircraft because it's a rigid body. They're all related with each other, and the math behind it is very, very simple. It's not rocket science. Okay, so then we are talking about another way of braking, the third way, and finally we will also look at in terms of breaking up the methodologies. We will do all of this in what is the classical parlance of Newtonian mechanics, though I'll also give you a shocker, at least for some of you, that Newton was not the original person who came up with these laws of motion, though we would like to give credit to him for all that he did, because perhaps he didn't have the information of this particular knowledge existing for more than 1.5 millennia before him. I will bring in those aspects as well a little later. But the way this course will progress is, as far as the first 3 points are concerned, we'll be only talking about the Newtonian mechanics, where we are dealing with all of this in a vector model, where you're talking about the cos, which is the force, related to the motion, which is in terms of its acceleration, and that's where, as I said, this ma comes into picture. Force is equal to mass into acceleration, which is a vector equation, because both force and acceleration are vectorial quantities, the mass being of course scalar. But on the other hand, when we bring in the rotation, we have a generalized version of that. We will bring in what are known as Euler's equations of motion. Euler being another great mathematician. Newton was not only a physicist but also a mathematician like Leibniz. Along with him, in fact, he introduced a whole body of knowledge called calculus, and even calculus of variations, where Lagrange, of course, also played an important part. But all those historical stories for probably another day, or maybe in the afternoon today. But right now, what we are looking at is the idea of, is that the only way? Newtonian mechanics of dealing with things as vectors, because as you know from your own studies, it's easier to deal with scalar quantities than it's dealing with vector quantities, because a scalar just has its measure number or a magnitude, whereas a vector not only has its measure number or magnitude but also a direction, and that direction makes sometimes handling vectors a little more complex compared to statics. Not that it can compared to scalars. Not that it's unbearable or impossible, just that the level of difficulty rises, and if you are open to it, it's not something that's so difficult, because you have been dealing with vectors for various other courses on a regular basis. But it's also possible to deal with the same thing in a scalar sense and get the same information out of it, and which is what the work energy method does. Of course, there's another vectorial way of doing it, equivalent to the Newtonian, which is called as the impulse momentum. And both of these are, you can think of it, because you would have already known Newtonian mechanics, you can think of it as derivatives from Newtonian mechanics. But it's like the chicken and egg story, or the seed and tree story, which came first. It's a never-ending argument. You can keep on arguing. At the end of the day, the conclusion will not be based on facts or truth, but who is the better debater amongst us, right? So whoever is a better debater, then you conclude that that is the way it was. The seed came first or the tree came first, right? But that's not the important point. These are equivalent of each other, okay? It doesn't matter which came first. In historical sense, of course, we can say which came first, but in terms of how these are laws of nature. So what exactly is happening? Because one is talking about the conservation of momentum in a sense, the other is talking about the conservation of energy, and the conservation of momentum cannot always happen, whereas the conservation of energy happens in a little broader range of problems, and therefore this is a little more reliable kind of a form than that, but nonetheless we can derive one from the other. So that's the whole idea. What do you do to derive from F is equal to ma? For example, a work energy principle is where once again we come back to the so-called independent variables. Okay, so remember we had the independent variables, which was space and time, which we together will call as space-time. Space-time is the four-dimensional field in which all of the dance that we are going to study throughout this course is going to happen on a platform, a stage on which this whole dance is going to take place, and which is why in the Indian cultural system we have the concept of Nataraja, or the king of dance. Essentially we are talking about the whole dynamics of life, as social dynamics, as you pointed out, is something that happens in almost an interplay of various aspects. If we understand the interplay of that aspects, life becomes such a beautiful way to experience it. Same thing with the dynamics of rigid bodies, dynamics of particles, etc. So that's the takeaway. So now why am I bringing that up? Because as I said, the independent variable is what modifies your Newtonian mechanics of F is equal to ma into work energy if the spatial dimension is multiplied on both sides. And because we're talking of vectors, you have to be very careful and say, is it a dot product or a cross product? And here it's a dot product. The dot product is F is equal to ma, F and a are vectors. You're going to dot it with ds, which is the displacement vector, and then you're going to integrate that. When you integrate the force with respect to the displacement vector, you end up with work. When you integrate the mass into acceleration with the displacement vector throughout the body which you are interested in, you end up with energies, in particular the kinetic energy that is over there, and therefore the work energy balance can be seen. People talk of these as almost entirely different topics, entirely different books written on it, etc. But you see the beauty of how everything falls into the same paradigm when you see that the impulse momentum is not very different. Here what did I do? I brought in these x1, x2, x3 along unit vectors, let's say b1, b2, b3. I dotted that with the force and the acceleration integrated in order to get my work energy principle. All that I do is to go to the other independent variable that I have introduced, the temporal variable, the time. And now if I integrate, now time is not a vector like your x1 b1 plus x2 b2 plus x3 b3. It's just a scalar quantity. So now I'm not talking about a scalar product or a vector product, that is a dot product or a cross product, but I'm just talking about multiplication. So when I multiply by an infinitesimal amount of time, like I did with an infinitesimal amount of displacement over here before integrating, infinitesimal amount of time, if I get the F is equal to ma and dot it with that and integrate, I get, when I integrate the force, I get a quantity, a new quantity, which for many of you it might, in this context of dynamics, might be a new concept. We call as impulse. It's an integral of f dt, that is the force times the time over which the force acts. And on the other side, mass into acceleration, when you're integrating with respect to time, you end up with what is known as momentum, because acceleration, remember, is the rate of change of velocity. Okay, so when you're integrating that with respect to time, it just becomes mdv from state 1 to state 2. It becomes, as if m is not changing, it just becomes m times v2 minus v1. It's essentially mv2 minus mv1, or even if m changes, like it does in the case of the aircraft, because you're burning fuel, remember, so the weight of the aircraft at takeoff and when you land is different. Even more so in the case of a rocket, when you're not only finishing up your propellants, but also it's a multi-stage rocket, so you're dropping off the stages which are already utilized, and therefore the weight drops not only in a continuous manner because of the propellant, but now and then in a discrete manner also, because you're dropping off an used up stage and retaining only the higher stages. So then you are talking about the momentum change that is happening and how that is related to the impulse. Even though I'm giving specific examples from aerospace engineering every now and then, I want to once again stress on the fact that these are much more basic dynamics concepts in engineering applicable to any other fields as well. Just that because we are in aerospace engineering and we are talking of an AE course, I'm bringing in those examples. Okay, so these are the two methods that actually come out of it. Maybe I'll just point out some of those things that I talked about in terms of the equation that is involved, because when you speak of equations, then very little gets retained, so it's nice to use the mathematical notations and put them up so that it stays with you visually as well. So this is the guy which was implicit in kinematics and came out explicitly in kinetics to get a relation between the cos and the motion, right? Now this is attributed to Newton. And equivalently, we have something in rotation, because we are talking not only of particles but also rigid bodies. And instead of force, there we will have the torque T, which is again a vector, because you can have the rolling moment, pitching moment, and the yawing moment. Okay, so those are related to I alpha. We'll use that notation for the angular acceleration. So these are what are known as translational, or sometimes also called as rectilinear, whereas this is your angular acceleration, right? Now this is mass, this is the inertia. So because we are dealing with vectors, we are essentially having in reality, the way these equations will be presented in a particular numerical implementation, once you choose the unit vectors associated with them, will be in terms of what we call as the column matrices for the vectors and square matrices for the quantities which are multiplying that. So in other words, you would have the second mass moment of inertia along the diagonal terms of this 3 by 3 matrix, and you will have the products of inertia along the off diagonal terms. Okay, and be very careful that it's a mass moment of inertia, not just the moment of inertia, which is a purely geometrical quantity, which we use, for example, Nafis is familiar with it, use in the structural analysis course. But here we are talking of mass moments of inertia, and therefore the weightage from the density of the materials which are part of the so-called rigid body that we have to deal with. So truly speaking, if we want to write this in a mathematically rigorous notation, I cannot write it this way, where I and m seem to be appearing as scalar quantities. They should be what are known as dyadics, which essentially is one level further in terms of the mathematical entity we are dealing with. We already know, going from a scalar to a vector, the major difference came in not only a magnitude but also a direction, which is what the vector has and the scalar doesn't. Now when you go to a so-called dyadic, you have to talk about two directions. For example, we talked about products of inertia. So the product of inertia, for example, one of the elements could be IXY. So it involves two different directions, X and Y, which is what we mean by two underlines over there, to put it in a very, very simplistic fashion, to introduce the concept of tensors, which scalar is a zeroth order tensor requiring no directions. Vector is a first order tensor requiring one direction, which is why we put one underline in its notation. And then we have the so-called dyadics, where we deal with a second order tensor, and we need two directions in order to mention that. In the case of the mass, it becomes kind of trivial because you're not really having that, but it's important to understand it from that perspective. And now that's not enough. I'm still not in a rigorous way of defining this mathematical equation. Remember, when I put two vectors next to each other and I multiply that, I cannot just say multiply those two vectors. I have to tell you whether it's a dot product or a cross product. Okay, so in that sense, this is a dot product that we are having between these two. Now this set of equations is mathematically rigorous. We're slowly building up the rigor to the math that is involved. But in reality, how this actually gets implemented is in terms of actual set of unit vectors that you introduce. See, this vector force, for example, I can, if I'm applying a force in a particular direction, I can introduce unit vectors either this way or some other way, and I can get totally different so-called components along each one of them, okay? But the total remains the same. It's my freedom as a analyst to introduce the coordinate system however I want, but the end result will not change as long as I'm consistent in my entire derivation, right? So that way, these are pristine, pure ways of expressing it, even without introducing the specific coordinate system, okay? But whereas once you want to utilize it numerically, for example, then you need to specify the coordinate system. In the case of vectors, you need one direction, and in the case of the dyadics or the second order tensor, we need two directions, and therefore once you specify them, these will become column matrices. Your alpha, A, T, and F, all the vectors will become column matrices, and your I, M, all these dyadics will become square matrices. And since we are dealing with three-dimensional space, these will be 3 by 3 square matrices, okay? So that's the important thing about this. Now what we talked about over here, that's as far as Newton is concerned, the Newtonian mechanics, or it's part of the classical mechanics. All of this is also still part of classical mechanics or classical physics, but it's a little more involved, relatively speaking, because the way in which, order in which we learn things. But as I said, it's the chicken and egg story. You can perhaps start from here and go to that as well, which is also very much a possibility, okay? So as I said, let's leave this equation for now. Whatever we talk about this is valid for that as well. Just that I will have to dot it with rotations, and rotation is one of the most complex things to represent, and we will talk about various ways of representing rotation. We're talking of three-dimensional rotation, that is. Single rotation, of course, very easy, but when you're talking of three-dimensional rotation, it's slightly more complicated. So we will leave this equation aside for now. We will take it up again when we get to rigid bodies and their 3D motion in particular, because the planar motion can still be dealt with, all the rotation as just a scalar quantity, and we can be pretty much done with it. But coming to, from Newtonian mechanics, how do we get to some of these things which are named after, again, great people like Lagrange or Hamilton, what we call as Lagrangian mechanics or Hamiltonian mechanics. All of that essentially comes from dotting this with the displacement vector and then integrating it, as I just mentioned orally earlier. I'm just writing that in explicitly in the form of an equation, okay? So F dot ds, where you're again having this displacement as different from distance, okay? Distance is a scalar magnitude of the displacement, but displacement, as you know, involves a direction as well. And what happens when I take a dot product of these is I'm looking at the point of application of the force, how much is it moving by in the same direction as the force itself. So for example, if I'm applying a force along the length of this particular thing, I'm not interested in what happens perpendicular motion, because that's not creating any work, right? It's orthogonal to each other and the dot product will become zero, okay? But it's what is the component of that, each of them, which is parallel to that, is what makes the difference. So that's essentially what we mean by the dot product over there. And if I'm dotting the left hand side with ds, obviously I have to dot the right hand side also with ds and make the same integration, of course, from one state or one location, let's say S1 to S2. The same thing we are going to do over here as well. Of course, there are various things that will be simplified out of this. I do not want to get into it, but let me say see, the acceleration is the time derivative of the velocity, right? Just like the velocity is the time derivative of what we will call as the position vector, okay? But the reason why I was hesitating to go to this stage at this juncture in the first class is because, once again, this is not a mathematically rigorous way of writing a derivative of a vector, okay? Just like here, I went in steps and started off with something not acceptable mathematically and finally made it mathematically acceptable to make this mathematically acceptable, I have to introduce what is known as a frame of reference. So a frame of reference is something with respect to which this derivative is taken. So for example, you are in this aircraft flying to Bangalore, you needed to use the loo. So you walked from your seat all the way to the toilet. So you're walking with respect to the aircraft, right? And then as an observer from here, if it was a glass aircraft, you'd see your total motion being the motion of the aircraft plus your motion on the aircraft, right? So there's algebraic sum of that is essentially taking place. So therefore, if I want to calculate your, let's say, velocity, which in turn is the rate of change of the position vector for you, then you would see that the velocity that I would have for an aircraft fixed frame is a very small magnitude of that velocity, because you're walking at a particular speed, let's say a few meters per second. But when I'm looking at it from the ground, algebraically it's getting added up with the aircraft's vectorial addition is happening with respect to the aircraft's velocity. So then it's a much larger magnitude that I'm dealing with, right? So the frame of reference plays a very critical role whenever you're taking the derivative of any vector whatsoever, be it position vector, velocity, acceleration, doesn't matter, force, etc. As long as you have a vector and you're taking a derivative with respect to a scalar, because time is a scalar, then you have to always specify with respect to which frame of reference you're taking that derivative. If this is not there, this is absolutely meaningless derivative that you're talking about dv by dt, okay? And of course, if it's a problem where x1, x2, x3 are also independent variables, then I cannot write it as d by dt, which is an ordinary derivative. I have to write it as a partial derivative, dou v by dou t, and even there it's important to specify what is the frame of reference. So this could be the, let's say, aircraft is flying over there, and then you have so I would call this frame of reference as I, and whether it's a rigid body or a frame of reference doesn't matter. This could be the earth for all you know. So this is essentially what we call as a frame of reference. The letter I that I chose instead of, let's say, E for the earth, I could have another frame of reference over here, which could be the aircraft fixed reference frame, and call the aircraft as A, and then I'll introduce A1, A2, A3 as the unit vectors along that, right? So now there's a frame of reference A, a frame of reference I, and whether I take the derivative with respect to one or the other, as we saw in our very simple example of walking on an aircraft, the value will be very different, not only the magnitude but also in terms of the direction, okay? So the direction of the vector could be quite different depending upon what you're essentially talking about, okay? So what we actually do in this case is we move the dt to the ds over here, then you have ds by dt, which is nothing but the position vector, how is it changing with time, which is nothing but the velocity. So you see this particular thing, so you have, if I rewrite that, that will be equal to m dv this is nothing but your v. So just like acceleration was the rate of change of the velocity, even before that you know that the rate of change of the position vector is nothing but your velocity, right? So now you have v dv, which is like v squared by 2, okay? So if you're integrating once again between those states, s1 and s2 was the position at those two locations, v1 and v2, let's say the magnitudes at those two locations. What you're essentially dealing with, of course, you have all these dot products. Yeah? So then we have an mv dv, and v dv will give you v squared by 2, and mass into velocity squared by 2, you know, is the expression for kinetic energy. Okay, so that's precisely what we have over here, kinetic energy. And here, you know, F dot ds is the force times the distance moved by the point of application of the force in the direction of the force. That is F dot ds integrated over the whole thing, and that's the work done by the force. So the work and the energy are kind of related to each other, which is what this does. Okay, we will go through all of this in a little more formal sense. Today's class is all about an overview, which is why I'm introducing some concepts without sometimes I'm trying to be as rigorous as possible, but there might be a little lack of rigor here and there. But once we go through the actual derivations, we'll do all of this in a little more careful manner, and then you would see that. So what is the second thing that we are looking at here? Impulse momentum, right? The impulse momentum method is nothing but in this whole equation you replace ds by dt. Okay, so that's when you do that, you end up with the impulse momentum equation, because f dt integrating the force gives you impulse with respect to time, and therefore on the other hand, on the other side you have the mass into acceleration times the time, and we saw this dt will get cancelled. You have just mdv, and that's integrated from v1 to v2. It's the change in the so even if mass changes, it will be m1 v1 minus m2 v2. Not so simple, but depends on how the functionalities are changing, the rate of fuel consumption, the specific fuel consumption, how it goes, how it changes, etc. All those things will be accounted for, but essentially you are seeing that there is a rate of change of momentum that is happening over there, and that's related to your impulse. So with this, I think, let me see what I have next. This I 10 minutes. Yeah, maybe I'll finish this slide. As I've already mentioned in the email that I sent to you 5 weeks back, we will not be using any textbook over here. In fact, I got your the copy of your textbook, which is used on campus, only just before the first day of classes last program, last study abroad program. So I have not had the chance to go through it in detail. So we'll not have any textbook. We will try to learn it from the very first principles, like the way I've been introducing you to it in this class. But you are most welcome to look at that textbook as well as so many other wonderful books that have been written on dynamics. Feel free, and if you have anything that you don't understand there, you can bring it to class. We can try to discuss and see how we can probably resolve some of those issues. Okay. As I said, this is what is used on campus for you. The suggested generic reference is McGill and King, Engineering Mechanics and Introduction to Dynamics. It's gone on already to the 4th edition, quite some time back actually. And the topics covered are once again put in the same thing that I discussed in the previous slide, but in a much more 1:1 correspondence with the chapters of that book is what I want to present over here. So that's the Newton's second law of motion, which is good enough for translations, but once we bring in the rigid bodies, we need have rotations as well, and therefore we need what is known as an extension of Newton's laws from translation or rectilinear motion, what we talked about over here, to angular motion or rotational motion. So that's what Euler does, Euler's laws of motion does for you. Okay, so to put it in a very, very simplistic way, it's the sum of forces. Remember, in statics also, you're getting to the resultant force and then you are setting it to 0, right? So the resultant force vector will have components in a planar motion, for example, along the x direction, along the y direction. So you have two scalar equations, and then you try to solve for the unknowns in terms of the knowns. So same thing over here, just that these forces can in general be functions of time apart from space. So you sum up algebraically over all of those force vectors, and then on the right hand side you have the time rate of change of the velocity. Once again, this equation directly taken from your book is not rigorous. As I said, whenever you're taking the derivative of a vector, you have to put the frame of reference. But sometimes there might be only one frame of reference in that entire problem or the entire chapter. So this might be an understood default value. So people might just drop it. So I have no qualms about that. But we as a class, whenever you're doing your homework, etc., and present it, I would want you to be very explicit about this so that you get into this habit. Very simple problems will have only one frame of reference, but most problems, even problems that you're solving as part of your homework, will have at least 2 frames of reference, in which case you need to mention with respect to which frame you're taking the derivative, because otherwise the results can be quite different from each other, right? So
How many homeworks are going to be given to us?
they're all there already in the files. You can go check them out. So
So I'm not able to join the group that is there.
is anybody else having that problem, or somebody has been able to join Teams?
I was able to join. You have to get off and then switch your school and click on your.
I tried that. No, I'm not.
So it'll load, and then if you go to like your profile,
Yeah, I know. I did try that already.
it should allow you to switch in the certificates.
I just going through the email that was sent.
Top right. I see this, and it says you are invited to join us or continue. Right? Then nothing. Oh! This is a normal one. Yeah. And I'm not on any week now. Maybe try me on.
Are you on? Which Wi-Fi are you on?
I'm on ISDS.
Classic technology.
What have you logged into with Teams? That's the usual Georgia Tech account.
Are you on the?
We can figure this out.
Okay, yeah. So let's just finish this slide and we'll break for lunch. So the time derivative, as I said, so there is a mistake on the slide. So in terms of the time derivative, I can't write it just this. I have to put the frame with respect to which it is taken. And the equivalent of that, just like velocity is a vector, the momentum is a vector as well. So in fact, we will call this particular quantity as P. That's the typical variable we'll use for this. P, a vector which refers to the translational momentum. Similarly, we will introduce what is known as an angular momentum, H, uppercase H, which we will be using for I times omega, right? Once again, M and I are put almost like scalars over here. That is another mistake with this. So this is essentially taken directly from your textbook. So just to show the possibility of these kinds of issues arising, because in our class we'll try to be as rigorous as possible, and if at all we are leaving out something, we will very explicitly state that it's a default and therefore I'm dropping it off, right? So then the thing that we already saw, when we want to take the derivative of this, I cannot just take m out of it, because m could also be changing with time, which is what happens, as we said, in terms of the fuel burn, etc., or a rocket propellant burn, and therefore it should be not only ma plus the m dot v that you need to bring in over there. Same thing over here, you can't just have I alpha, but also the I omega dot that needs to come in the appropriate way. Okay, we will go into those additional terms, etc., later on, right? So that's the typically the kind of things that we will talk about to start with in the first few, maybe the first week and the little bit of the second week. Once we are done with that, we will go into, so we're kind of probably starting a little with your second chapter and then going into your first and second chapters in terms of, as I said, I'm not taking the content from there, but if you want to go and cross verify with that or enhance your understanding, so then this kind of cross link with the chapters in the book might help. Okay, so as I said, we'll be dealing with the motion of the simplest entity that can be, which is zero sized one, namely the particle, and then we will move it to once again this translations, but translation not of particles but of a particular point in the rigid body, namely its mass center. And there could be multiple bodies that you're dealing with simultaneously in a system of bodies, and then you're talking of the their mass centers. Okay. Then the next thing that we look at is the kinematics of planar motion of the rigid body, wherein the additional complication that we introduce what McGill and King introduced in chapter 3 is in terms of one rotation being one measure number or component of the rotation being brought in for that. Okay. Then we will talk about in chapter 4, where we're looking at the costs, the force and the moments which are causing this translation and rotation. So we'll try to bring them into picture once again for planar motion. So things will remain very simple as far as rotation is concerned, but remember, it is innocuously simple. Okay, it's not in reality so simple, just that we are considering a very simplified problem, therefore it is so simple. Otherwise, as I said, the rotation, if thought of as a vector, is one of the most complicated things to deal with, especially finite rotation. Infinitesimal rotation, it's fine. But if you're looking at finite rotation, which is what we experience in reality for an aircraft or any flying vehicle, then it's quite complex. Okay, but there are ways to handle it, and we'll look at some of the simple ways to handle it. Okay, then coming to the last thing that we'll probably be doing is to enhance it to the overall problem of the rigid body aircraft, a rigid body model of an aircraft, because the actual aircraft is not rigid body, it's flexible as we discussed, but we will look at its 3D dynamics, not planar or 2D dynamics. Planar is 2D. Now we bring in the additional dimension, but that brings in 2 more rotations, and therefore rotation can no longer be dealt with as a scalar in our derivations, but as a finite rotation vector. Okay, I think I'll take this up in the afternoon because this is too scary for lunch. 2.